Good morning, students. Mr. Carver here. Today is 6.7. Today we'll be exploring fluid force. In the 1600s, French mathematician Blaise Pascal discovered what every 5-year-old has discovered when diving into a pool, and that is fluid force increases with depth. What most 5-year-olds don't realize is that the fluid force is also determined in part by the liquid into which you're diving. So diesel fuel might have a much different fluid force being exerted on your head than, say, a vat of milk. So today what we're going to do is explore how to determine the combined fluid force on a horizontal plate, and then use calculus to determine the fluid force being exerted on a vertical plate. Let's start off with a cubical tank, 12 feet on the side. And let's say that I've got a door at the bottom of this pool. And let's say the door is 4 feet by 8 feet. Fluid force is defined as density times depth times area. You'll need to memorize that. Density times depth times area. Let's say that this is a saltwater pool. Salt water has a density of 62.5 pounds per cubic foot. So if I calculate the fluid force being exerted on this door that is located at the bottom of the pool, door opens out. It's an easy calculation because the entire surface of the door is at the same depth. So I've got density, which is 62.5, times depth, which is 12 feet, times area. And in this case, it's going to be 4 times 8, or 32 feet. Square feet, rather. So that gives me a total of 24,000 pounds of force being exerted on that door. The problem becomes a little more difficult if I then move the door or relocate the door, drain the pool, relocate the door maybe to the front of the pool. Again, it's the same cubical tank, 12 feet on a side. Now I've got a door that looks something like this. It's still a 4 by 8 foot door. Again, opening outward, same salt water contents in the tank. This becomes a much different problem because, as you notice, the top of the door is 4 feet deep, the bottom of the door is 12 feet deep. Every portion of that door is at a different depth. So the way that we're going to use calculus is we're going to think about subdividing this door into an infinite number of infinitely thin doors going from 0 all the way up to 8. And as I mentioned in previous sections in this chapter, the x and y axis can be placed arbitrarily anywhere in this picture. I think it's probably easiest to put the x-axis at the bottom. We're dealing with basically positive then distances. It's still the same guiding formula, right? Density times depth times area. So we're starting off with 62.5. I'll be integrating. We're using the summation powers of integration, going from my low y of 0 all the way up to the upper y of 8. That's where my infinitely thin doors will be located. And incidentally, the reason that we're doing this is because this door, this red door here, is so thin that the top of the door is essentially at the same depth as the bottom of that door. And what I'll be doing is combining the fluid forces of all of these infinitely thin doors from the bottom to the top, thereby giving me the combined fluid force of all of them. So I'm integrating from 0 to 8, that is low y to high y. Depth then, of course, of this door, I can look at it as measurement from the surface down to the individual thin door that I'm using. So just like in disc, shell, and washer, that depth is going to be 12 minus y, because I'm not measuring from the x-axis. And then the area of the door is not the area of the complete door. Remember, it's only the area of my infinitely thin slice of door, that piece right there. So it is 4 feet wide and it is dy tall. So I have density, I've got my depth, and then these two things constitute my area. And that will, of course, be in pounds of force. Let's take a look at another example. There are other places where symmetry is required. So let's say that I've got a porthole in the side of a boat. Let's call it 2 feet, 4 feet rather, in diameter. And let's say the center of that porthole is 42 feet above the surface of the ocean. I'm going to place the origin right at the center of that circle, just out of convenience, because then the equation of that circle will be x squared plus y squared is equal to 4, or radius squared. And again, what I'm doing is, because the top of the window feels less pressure than the bottom, because the top is less deep than the bottom, what I'm going to do is break this circular porthole up into an infinite number of infinitely thin rectangular portholes. And I'll use the magic of integration to combine all the fluid forces being exerted on those little thin slices of window. So what I'm going to do is integrate from -2 to 2, and that is where my thin slices of window exist. I think I said that this is 42 feet below the surface of the ocean. That is from y = 0 up to 42. Again, this being my x-axis. Density, let's call this the ocean, 62.4 pounds per cubic foot. That's going to be given in the textbook. I'll also give it to you in on test or quizzes. Density times depth. Depth, just as it was in the last example, goes from the surface down to the window. In this case, this is 42 minus y, which incidentally also agrees with my interval of integration. The topmost window is at a depth of 40 feet. That's 42 minus 2. And the bottommost window is going to be at 44 feet, 42 minus a -2. So I've got density times depth and now times area. And I need to use symmetry here because I've got a circle. Rightmost curve minus leftmost curve will leave me with 0. So this distance from here just to there is x, and I want to double that. So this is going to be 2x wide times dy tall. All of this being my area calculation. Now, obviously, this is a dy problem, which is where this formula is going to come in. So my final answer will be 62.4 integrated from -2 to 2. This is 42 minus y. And I've got then 2. And my x now, in terms of y, becomes 4 minus y squared times the height of those rectangles, which in this case is dy. Setup only would give you an answer like that. Of course, if I was doing this on the graphing calculator, I would put the 62.4 back in, combine it with the rest of this. All of this will go into y1, and then I'd integrate from -2 to 2 on my graphing calculator. All right, hope that helps, and have a great day. Thanks.